So I'll be talking about dimension, and the idea of dimension is based on the fundamental quantities. But among the seven fundamental quantities in physics, I will only be making use of what? Four of them. The first one I'll be making use of is what? The mass, represented by what? M. I'll make use of current, represented by what? I. I'll make use of what? Time, represented by what? T. The other one is what? Displacement. I can write it displacement, distance, and length. So it can either have these three of these names represented by what? L. So apart from four of them, which is a four things I'll be using, there's a little bit modification in this fourth one. So any question you're solving and the formula involves area, use L raised to power 2. If the question involves volume, use L raised to power 3. So these are the only tools I'll be using. And you are required to at least know the formula of the parameters involved. So let's begin with our first example. I'm going to begin with what? Velocity. So for the velocity, if I am required to get the dimension of what? Velocity. We know that velocity is given as what? Either I put distance or displacement over what? Time. Distance, like I've written earlier, is represented by what? L. The t is what? The time. So I'm going to have L times what? 1 over t. Bringing this t up, I will have what? L t raised to power minus 1. That's the dimension of what? Velocity. Let's say I need a second one, which is what? Acceleration. Linear acceleration, to be precise. We know is what? Velocity over what? The time interval. So the velocity that is given as what? L t raised to power minus 1 according to the dimension. Then we have the time to be what? T. Bring this one up, I'm going to have L t raised to power minus 1 times what? 1 over t. Okay? I have L t raised to power minus 1 times what? T raised to power minus 1. Applying your laws of indices to that t, because the base are the same. All I have to do is just add the powers, because it said that what? Whenever the base are the same and they are multiplying each other, simply add up the powers. So I have L t raised to power minus 2. That's for acceleration. Let's say I want to get the dimension of what? Force. Force is given as what? Mass times what? Acceleration. Now, we know that what? As I told you that mass will be what? M. So I have m times what? The acceleration, which is what? L t raised to power minus 2. So multiplying two of them, I will have ml t raised to power minus 2. So let's take another one, which is what? Density. We know that what? Formula for density is what? Mass over what? Volume. Mass is given as what? M. Volume is given as what? L raised to power 3. Bringing this thing up, I have ml raised to power what? Minus 3. So let us include other quantities like what? Pressure, power, work done. We know that what? Formula for work done is given as what? Force times what? Distance. But the force on its own, as earlier gotten, which is still on the body, is what? ml t raised to power minus 2 times the distance. Just multiply the L together. So I'm going to have ml times L t raised to power minus 2. I have ml squared t raised to power minus 2. Then let's take that of what? Pressure. We know that what? Pressure is given as what? Work done. No. It's what? Force over what? Area. Sorry about that. Force is given as what? ml t raised to power minus 2 over what? The area, which is L squared. One of these will cancel one of these. I only have L left. So bringing the L up, I have L raised to power minus 1, T raised to power minus 2. Now let us start including what? Electrical quantity. So the first electrical quantity I shall include will be what? EMF, or terminal potential difference. The word EMF is used when the circuit in concern is open, or we use terminal voltage when the circuit is what? Closed. So for this EMF, we're given as what? Work done. That's the work over what? Charge. And charge is given as what? Current times time. So for work done, which is still on the board, I have ml squared t raised to power minus 2, then divided by what? The charge, which is what? Current multiplied by time. So bringing them up, I have ml squared I minus 1. This will come up, I have t raised to power minus 2 times what? T raised to power minus 1. These, since the bases are the same, just add up the power. I have ml squared t raised to power minus 3. That's the dimension of what? The EMF. Please include the I bar, that's minus 1. That's the dimension of what? EMF. Now, also, another one I want to talk about is what? The capacitance. For the capacitance is given as what? The charge. Charge, which is this way, over what? EMF. But the charge on its own is what? That's I with what? T. Then the EMF is still on the board. We have ml squared t raised to the power minus 3 multiplied by what? This. So bringing these people up, I will have m minus 1, then the L minus 2. When the T comes up, I have T 1 plus what? 3. When the I comes up, I have I 1 plus what? 1. So on that note, I'm going to have m minus 1 L minus 2 T raised to the power 4 I squared. So another one I want to talk about is what? Resistance. Resistance. For resistance, you can get it from what? Ohm's law, which you said that what? That the terminal PD is equals to what? The current multiplied by what? R. Making our result formula have V divided by what? I. Our V or EMF is this, which is what? ML squared. I have T raised to the power minus 3, I minus 1, divided by what? The current. The current comes up, I have what? ML squared, T raised to the power minus 3, I have I minus 1. That's when this one comes up, I have another minus 1. So I am going to have ml squared t raised to the power minus 3. Addition of the minus will give me what? Minus 2. So since this is a what? The dimension of what? Resistance. It simply implies that what? Since resistance can be used interchangeably with what? Impedance as well as what? Reactance. Simply means I can say that they all have the same dimension, which is what? ml squared t raised to the power minus 3, I raised to the power minus 2. This reactance can be what? Capacitive reactance or what? Inductive reactance. It's called capacitive reactance when it's what? The opposition to the flow of current offered by a capacitor. And it's called what? Inductive reactance when it's the opposition to the flow of current offered by what? An inductor. So we can actually use the same dimension to verify the equations of motion. And how do you do that? Is when the dimension you have on the right hand side balances the one you have on the left hand side. And you must ignore what? All constants. All constant. What I consider constant here is what? Any other parameter that is not among the 4 basic quantities that I have listed for you. So let's take a typical example. For the first one, I have u plus what? 80. So if that is true, for that of v, I have what? L t raised to the power minus 1 is equals to what? L t raised to the power minus 1 plus what? Acceleration, which is what? L t raised to the power what? Minus 2 times what? T raised to the power 1 there. I have L t raised to the power minus 1 is equals to what? L t raised to the power minus 1 plus adding the powers of the t. I have L t raised to the power minus 2 plus 1. I have L t raised to the power minus 1 is equals to what? L t raised to the power minus 1 plus what? L t raised to the power what? Minus 1. One of these plus one of these. I think I'll have 2 of that. That's 2L t raised to the power minus 1. Since the dimension that is here is the same as the dimension here, ignoring these two simply means I've established that is what is correct. So let's take what? The second equation of what? Motion. So from that one, I will write something that looks this way. S is equals to what? Ut plus what? Half at squared. The S is distance, which is L. U is velocity, which is what? Raised to the power this. Times what? T plus 1 over 2. Acceleration is what? L t raised to the power minus 2 times what? T squared. So from that note, I have L is equals to what? This one has power 1. So add them together. I have L t raised to the power minus 1 plus 1 plus 1 over 2. I have L t raised to the power minus 2. Add the powers again because they have the same base. So I'm going to have LT, okay, only the L, minus 1 plus 1 is 0. So I have LT raised to the power 0 plus 1 over 2. LT raised to the power minus 2 plus 2 is same 0. And from your laws of indices, anything raised to the power 0 is what? 1. So this can cancel this. I have L is equals to what? L plus what? L over what? 2. So simplifying this part, I have L is equals to what? 2L plus what? L. So from that note, I will have L to be equal to what? 3L over what? 2. If I should ignore this 3 over 2 or 1.5, you can see that what? L is equal to what? L. Taking the third equations of motion, so we will see as well, right? Actually what? Pan out. So we have v squared is equals to what? U squared plus what? 2as. Our v squared is what? L2 raised to the power minus what? 1 with squared now. I have L2 raised to the power minus 1 with what? Squared plus what? 2 times what? L2 raised to the power minus 2 times what? L. So from that note, I have L squared t raised to the power minus 2 is equals to what? L squared t raised to the power minus 2 is okay plus this and this. I have what? 2L squared t raised to the power minus 2. So from that note, this and this are exactly the same, only that this 2 of this plus 1 of this. I have L squared t raised to the power minus 2 is equals to what? 3L squared t raised to the power minus 3 minus 2. Since these and these are the same, I can say they are correct. So ignoring what? These 3 there. So that is how to use them to what? To verify whether any formula is correct. You can try them on any formula that you know, and you can use them to establish what? Relationship between what? Parameters of what? A formula that you don't actually what? Know. Thank you for watching.